Okay, so let's see. So this is what we were discussing. So when you go into reverse bias, what happens is the exponential V goes negative, and then this is the reverse current that you get here. And we are trying to understand how this reverse current really flows here. Okay, so for that, we just said that if you look at excess hole density at the edge of depletion region, the excess hole density is minus, which means the region is deficient in carriers, minus Ni square over Nd. And the excess electron density, on the other hand, is minus Ni square over Na. And so this is the plot that we have. Okay, delta Px goes like this here, and delta Nx goes in this particular manner here. Now, note that this is delta. The actual hole density at this particular point would be what? Delta Px plus the equilibrium value. And what is the equilibrium value? Ni square over Nd. So what are we saying? What is the hole density at this particular point? Almost like zero, negligible. And then as you go into the, deeper into the bulk here, the hole density will go back to Ni square over Nd. So this is the picture that we have. That was excess hole density, which goes negative here, and then it goes to 0 here. And now this is the total hole density here. So this goes here, right? And this the electron density here. All right, so that's the picture that I have. Of course, it's not going to go to exactly 0. This is a simplified picture here. So now, how does this current flow then? We have said that, for example, this part of the current, this is the total reverse current. This part, as we said, originates from the N region. And this part originates from the P region here. So let's try and understand how this particular current really flows here. And remember, in our derivation, we have said it's a diffusion current. All this minority carrier current is a diffusion current here. But note, if I take Px and I take its derivative, if I take the derivative here, it's 0. Right? There's no diffusion current. But we are saying holes are diffusing, holes are going from N to P. But at this particular point, if I take the derivative, there is no hole current. Jp is del P by del X here, the derivative is 0. But then at this point, we are saying there is a hole current here, at this point here, right? Which is equal to here, dP by Lp Ni square over Nd. Where is this coming from? No, the holes only. We are talking about holes. Holes are minority carriers. And note that holes have to start from here. And we are saying diffusion current is 0, which means no holes are going from here. But then we are saying there is a hole current here, right? And the hole current is of this magnitude. This is the hole current which enters the depletion region, comes out from this side here. So where is this current coming from then? If no holes are coming from here, but then there is a hole current here. Where is this coming from? The generation process here is the reverse here. So what is happening is now, let's look at this process here. Let's look at a region close to roughly a diffusion length from here and a diffusion length from here. You see diffusion length, but the concept of diffusion length, a qualitative concept that you should keep in mind, is the average distance a hole travels before recombining. Okay, so if you create excess holes here, for example, let's say this region is the extent of this region is depletion region here. Oh, sorry, the diffusion length. If you create a hole here, the hole has a chance of coming here before recombining. But if you create a hole somewhere further away, the hole has less of a chance to enter the depletion region here. Okay, so anyway, let's see how the carriers flow here. So we are looking at this particular region, which you can see here in this part here, this part. And what happens is you create carriers. Generation is all the time taking place. So you create excess electron, you create an electron in a hole. Now you create an electron in a hole, and what happens is there is a diffusion process because there's a gradient. So the hole starts from here and moves here. The hole moves here. Note that it diffuses till this boundary. The moment it comes into the depletion region, there's a field which simply sweeps it away. Okay, so sweeps it away and it comes here. And once it comes here, it's a majority carrier. There's no problem. Majority carriers move easily. Okay, the electron, of course, goes here. And then in the external circuit, of course, what happens is the electron starts from here, goes here, comes here, and the two recombine. And you created an excess electron in the hole. That's how they moved, gave rise to a current flow, and then they recombine. And then this process keeps on occurring. So you keep on getting generation here. You generate electron hole pair, the electron goes here, the hole goes here, and eventually reaches here. The electron then flows through the circuit, comes here, recombines, and then you get a current here. So the current that you get, reverse current that you see here, is a generation current. It comes through thermal generation. Because otherwise, you see, from here, there are no holes going. Right? There are no holes going. So where are the holes coming from? Well, they're getting generated in this region here. Okay? And so reverse current is due to thermal generation and diffusion. Carriers, again, if you go back here, the first part is here is generation. So you're generating carriers here. The second part, this hole in this region here, note is a neutral region and the hole diffuses. Okay, and this is the bottleneck. Once it enters the depletion region, then it's not a problem. The electric field sweeps it away and no issue there. Okay, so for that reason, what we are saying is reverse current is due to thermal generation and diffusion. These are the two processes that are occurring, giving rise to this current here. Okay, now this current, of course, we have arrived at a particular route. We have done the derivation and we have come to it. Let's do it through an alternative route here. And so the idea is as follows here. We have said that generation, recombination, generation are all given by this complicated expression, Shockley-Hall-Reed recombination. And note, if you look at this recombination, we have two terms here. We have NP and Ni square. N into P, the first term describes recombination. The second term, minus Ni square, describes generation. In equilibrium, we know NP equal to Ni square. Recombination balances generation. Okay, so either I can write recombination like this. Alternatively, you can also think of R equal to minus G, which is same thing as negative of generation is nothing but recombination. Okay, so negative of recombination is generation here. All right, so this equation that you see here, it describes not only recombination, describes generation also. Okay, the second term is generation, the first term is recombination. All right, equilibrium, they balance each other. Non-equilibrium, of course, then one is larger than the other here. So as we said that we are taking a simplified case where we assume that the defect which is carrying out recombination is in the center of the energy gap. So ET is 0. We have taken P, tau n equal to tau P equal to all same. And therefore we get recombination equal to Pn minus Ni square n plus P 2Ni tau inverse. And as I said, recombination is minus G here. Is the same thing as. So now when you apply a reverse bias, what you are doing is, note the following, in a reverse bias, the product of P and N in these regions here becomes less than Ni square. When you apply forward bias, the P into N becomes Ni square e to the power QV by KT. It becomes larger. When you apply reverse bias, the product becomes smaller. So both P and N become smaller than Ni square. So we neglect it. We get Ni square here. And in the bottom, if we are looking at this region here, the dominant term is N, which is practically equal to Nd. So what we get is minus Ni square over Nd into 1 over tau. Note that I have a minus term, which effectively says that I have generation occurring in this region here. Okay, carriers are getting generated here. So this is the generation rate. All right, the generation rate of carriers in this particular region here. So G equal to Ni square over Nd 1 over tau. And then what we are saying is the following. So you generate carriers here, you generate electrons and holes, but holes which are within it, now remember you are generating holes and they can recombine also. But holes which are within the diffusion length can actually reach this particular depletion region and escape and give rise to current. So you are getting a generation all over like this here, but only within this region can they contribute to current. Okay, so what we are saying is that you take a length equal to LP, diffusion length, and you look at the generation rate in this region here. This is generation rate per unit volume. If you multiply it by LP, you get total number of holes which are generated in this region. And we are saying these holes then can go into the depletion region and then give rise to current. And therefore, my current then is this generation rate that you see here, Qni square over Nd 1 over tau multiplied by LP. LP is the total length over which generation is taking place and can contribute to current. And when you do that, then you get a current here, which of course should remind you of the first term. Right? So as I said, this expression for reverse current we obtained through another route, but now we are also trying to tell you how this current is flowing by talking in terms of generation. This generation of carriers here occurring, generation rate is here, and this generation rate multiplied by this region's length is what contributes to reverse current. Okay, and similarly now you would expect the following here. If generation here gives rise to a current like this, then I will have a generation here. In this region, electrons and holes are generating. And what happens is the electrons now move into the depletion region here. They diffuse into the depletion region and they come here. So that's what is happening here. So similar generation rate here is Ni square over Na, 1 over tau, and it occurs over a region of length Ln. So we multiplied by total generation, which is this one, multiplied by L, effective length, multiplied by Q, and that gives us the total current here. So this is the current that is coming from generation here, and this is the current that is coming from generation here, and you add them up, and of course you get the total current. Okay, so that's the source of current. The reverse current is what? A generation current. Generation here and generation here. And I'm sure now it must be bothering you. You're taking generation here, your generation here. I'm not taking generation here. Why? Because the holes will not be able to reach here. They are away by more than a diffusion length, and therefore you generate, but they recombine. So they don't reach here. I'm not taking it here, but because again they don't reach the depletion region here. What about generation within the depletion region? I should take that into account, because if I create an electron and a hole pair, there is a field. The field will push the electron here. The field will push the hole here. So I should take generation within the depletion region also, right? So you are generating carriers here. Of course, it's easy for an electron to go here, the hole to go here, because the field is separating them out. Okay, so I should take not only the generation due to here and here, but I should also take generation within the depletion region. And therefore, I should add one more term which comes from generation here. So now 3 sources of reverse current you are seeing: generation here in the N region, generation here in the P region, all within the diffusion length, and generation within the depletion region. So this is something that I need to add to my expression to get a final value. So let's do that. So what we want to do is calculate what is the total generation rate. So again, we need to go back to this equation here: Pn minus Ni square n plus P plus 2Ni 1 over tau. That gives you the generation rate and recombination rate here. Again, P and N, when you apply reverse bias, is much less than Ni square. So I ignore P and N. And since we are in the depletion region and we are under reverse bias, which means P and N both are much smaller than Ni, because we are under reverse bias condition here. Okay, so note that the moment you have electron hole pair, the electron hole pair are swept aside. So both N and P are smaller than Ni, and therefore you can ignore them also within the depletion region, and you get only 2Ni in the denominator. You get minus Ni square here. So the net generation rate within the depletion region turns out to be minus Ni by 2 tau. And now all that you have to do is, this is the net generation rate at any point in the depletion region, multiplied by Q and multiplied by the total width of the depletion region. And you get the net generation current within the entire depletion region. And so this is the extra current that comes in because of generation here. And so the total current then, reverse current, is the first term, which is there due to generation here and here, and the second term, which comes about because of generation here. Okay, so that's the total reverse current that is there. All currents are generation currents here. Electron hole pairs are being generated and they get separated. The electrons move towards the N side, the holes move towards the P side. And that's how the current flows. Let's look at the values here, typical values here. Okay, so we've been taking a PN junction like this, a symmetrical PN junction. Doping is 10 power 16 here, 10 power 16 here, 5 times 10 power 16 here. And we know now these are the 2 components here. Let me give you the values. I've given you dP, dN, all these values have been given to you earlier. So let me calculate the numbers here. This part is 1.75 into 10 power minus 11, and this part is 1.9 into 10 power minus 7. Okay, look at the numbers here. Within the depletion region, it is 1.9 into 10 power minus 7 and 1.75 into 10 power minus 11 here. This is 3 orders of magnitude higher, 4 orders of magnitude higher, right? So most of the reverse current, where is it coming from? It's all coming from here. All coming from the depletion region. So carriers are getting generated here and they get separated and they give rise to the current here. Okay, so that's the dominant current here. Generation within the depletion region here. Now this is for silicon. Now suppose I do the same calculation keeping everything same, but I decrease the band gap. Silicon band gap is 1.12. I decrease the band gap to 0.7. Everything is the same. What changes? Ni. So when I decrease the band gap, what am I doing? I'm increasing Ni. So if Ni increases, whose importance increases? The first term. The first term is Ni squared, the second term is only Ni. So the importance of the first term increases. So if I do the same calculation, everything same, only change the band gap, then I get the following values. This first term becomes 1.8 into 10 power minus 4. This becomes 6 into 10 power minus 4. This is still a little larger, but now they are comparable. And if I reduce the energy gap even further, what would happen is the first term becomes dominant. So the reverse current will then be determined by all the generation which takes place outside the depletion region. Right now, it is taking place all within the depletion region. Okay. Now, this is also a source of difficulty. The difficulty is as follows. Many times, you guys have done 380 experiment, and in 380, we asked you to measure the current versus voltage characteristics of a PN junction diode. And what you do is you apply various forward bias, 0.4, 0.5, 0.6, and all that, and you measure current. And then, of course, if you neglect the higher current region here, you see a nice exponential, and you fit the exponential, and you find J equal to whatever, let's say, 3 into 10 power minus 11 exponent QV by this KT. So you measure forward current, and you fit it like this here, right? And you obtain this current here. Now, when you look at this one, what do you expect? You expect that this will be your, we tend to call it reverse saturation current. You expect that if I reverse bias my diode, I should get this much current here. But you don't get. Go any silicon diode, PN junction diode, measure the characteristics, fit it, and you get this expression. We tend to call it reverse saturation current. Now take your diode, reverse bias it, actually measure the current, you will not get this. Where is the flaw? Where is the mistake? The mistake is, note that what is this value here? This value, if you go back and look at our currents, we said, if you go back and look at our expression for current, let's go back to here. We said our current is in forward bias like this here, right? In forward bias, the current is made up of QV by KT and QV by 2 KT. Now, when I go to sufficiently large bias, this is not important. All that I get is this term in forward bias, right? This term in forward bias. And now this is what you're fitting. So when you're fitting and extracting, what are you getting? This part here. This is the part that you're getting, and you're calling it as the reverse saturation current. Q dP by LP, Ni square over Nd and all that. What does, in reverse bias, what does this represent? Generation outside the depletion region. And that's not the dominant term. Okay. So if you go and fit your forward characteristics, obtain this particular value, and you say my reverse current is going to be this one, that's not true. Reverse current is not going to be this one. Okay. Reverse current is going to be much larger than that one. Okay. So that is a point that's important in silicon and many other diodes, that the current that you get from here is just, this value is only for forward bias. It's not for reverse bias. Okay. It only indicates maybe the generation outside the depletion region here. So you need to go and measure the reverse current. Then only you will get this particular value. So the reverse current is going to be this value here, which is much larger than this particular value. Okay. And you can see here, in this case, is 4 orders of magnitude larger than this one. Now, reverse current, of course, you would like reverse current to be small, right? We don't want a PN junction to have a lot of reverse current. So how do we keep reverse current small? If this is where it comes from, how do you keep reverse current small? What do you want? Well, tau to be very high. Tau is lifetime, carrier lifetime. So you want it to be very high. Now, it turns out, if you look at lifetime of carriers in a semiconductor, it depends on the doping. Doping is like adding impurities. The more the doping in a semiconductor, the less the lifetime. Okay, so you would like lifetime to be as high as possible, which means you would like your semiconductor to be as pure as possible. So the purer the semiconductor, the less the doping in the semiconductor, the higher the lifetime. Okay, and then you get a lower reverse bias current here. What are the other means? If you were making a PN junction diode and you wanted very low reverse current, what else will you do? Try to make a very pure semiconductor with high tau. What else? Depletion region. Well, depletion region, you would like to keep it small. How do you keep it small? What do you do? Depletion region depends on what? For a fixed applied bias, depletion region depends on the doping. So you would like to keep the doping high, right? So doping high, depletion region becomes small, but doping high is making your tau problematic, right? Not only that, we'll see later on, if you're interested in reverse characteristics, you want breakdown to be high also. Now, the moment you make doping high, the breakdown voltage goes down there. So you don't want to make doping to be high. So we have seen now the third factor is staring all of you in the face. Tau is there, W is there, and Ni, intrinsic carrier concentration. What do you do here? How can you make Ni small? So that's why you find that the diodes which have very good reverse characteristics, people want to go to larger bandgap semiconductors. So silicon may not be the best choice. Going to, for example, silicon carbide, gallium nitride, these are large bandgap materials, so their Ni is much smaller. But for silicon now, if you choose silicon and you want a smaller Ni, what do you do? Choose silicon and smaller Ni. How do you get smaller Ni with silicon? How do you get less dark current in silicon by lowering Ni? How do you lower Ni? Ni depends on square root NC e to the power minus Eg by kT, 2 kT, right? So temperature. So you decrease temperature. You decrease temperature and the reverse current goes down. Reverse current goes down. And don't think that, that you can't decrease temperature. I mean, there are many applications we'll just talk about where you do deliberately, for example, when you're using a PN junction as a photodetector. Okay, we'll just see when you use PN junction as a photodetector. This one is what we have when you don't have any light shining. So this is the dark current. And you want the dark current to be as low as possible. So what do? You take your PN junction detector and put it in a liquid nitrogen, for example. So if you put it in liquid nitrogen, the temperature goes 77 Kelvin and temperature is really low, Ni comes down. Ni is exponentially dependent on temperature. This current will go down drastically. So the reverse current then, so these are the factors through which you can control here. Okay. All right, so let's move towards the detector. So that's an interesting application of a PN junction diode. So we have obtained a reverse current given here. And the same reverse current now, I've written it in this form. We've said the whole reverse current can be written as Q times generation rate multiplied by Ln plus Lp, generation here and generation here, plus Q, some generation rate, I should have put a different generation rate within the depletion region, Qg multiplied by W. All right, so it's all coming because of generation, the reverse bias current here. So now it's very easy to see that this is all coming from generation and this is all thermal generation. Normal carriers which are being generated by thermal means here. Now it's easy to see now if I shine light. If I shine light, what will it do? It will also create generation, right? And suppose the generation rate is GOP, G due to optical source here. So if the generation rate is GOP, for simplicity, let's assume that it's generating everywhere uniformly, GOP here. How will my current change then? What will happen to my current? See, that's why this equation I've written in terms of generation rate. So earlier it is only G thermal. Now it will become G thermal plus GOP. That's it. So this will become G thermal plus GOP. This will also become G thermal here plus GOP. So what will happen to your current? So PN junction will become a photodetector. And so you will get G thermal, which is all this part here, plus you will get Q GOP multiplied by Ln plus Lp plus Q GOP multiplied by W. So you get an additional current. The optically generated electron hole pairs, the hole will go here, the electron will go here, and you get an additional current. Because reverse bias current is generation current. So now you've added another source, and that gives rise to its own current here. So you get a current which is due to thermal generation, which we are calling it as dark, and you get a current due to light. The light here, QGOP, Ln plus Lp, and QGOP into W. Now, of course, you would like, as I said, now you are seeing that I would like to keep my dark current as low as possible. I want my reverse current to depend entirely on light, and therefore I want to keep dark current small, and dark current small, dark current is coming from here in this part. This is my dark current. And how do you keep dark current small? Well, you choose a high purity material, tau is high, and maybe you cool the semiconductor, cool your detector to make Ni small. And therefore, you can minimize your dark current here and then get a current which is more of this. So here is PN junction is acting as a detector of light here. Okay. The other way of doing it, you know what happens? Another way of what we do here. So when you use a detector, now remember detector, let's say if you look at say fiber optic application, right? So the message is being sent through light, and the light is not constant. The light is being pulsed, right? 1 and zeros and all that. So light is being pulsed. So your detector has to respond. It has to respond to the light. Now imagine that you have the light is on and you create an electron hole pair here. Now hole has to go where? The hole has to go all the way, diffuse all the way here into the depletion region and then come here. Now diffusion, you can imagine, is a very slow process. So the light is on, you create electron hole pairs, and then suddenly you switch the light off. What happens? This electron hole pair didn't get a chance to reach here at all. It will not respond because diffusion is a slow process. While generation within the depletion region, what happens? I have a high field which immediately separates it out. So that's a fast process. So when you're making a photodetector and speed is important, you want generation to take place within the depletion region. And you want most of your current to come from within the depletion region and not from here. Because those, carriers here will take time and carriers here will take time and the whole detector becomes very slow. So you want it to be generated here. So now the issue is, how do I make my depletion region large? For a given reverse bias, how do I make my depletion region large? Okay. One way that people do it is, you reduce the doping. One way that you see here is like here. You have P and you have N and you have I. Intrinsic region in between. You create a region here. Now, you get a depletion region here. You get a depletion region here. But this entire region, what do you have? You have a field. Note that P region will have what? Negatively charged acceptor atoms. And here you'll have positively charged acceptor atoms. You have a field. And this I region has a uniform field. And now you can make this I region thick. And so therefore you get a region which has a large field and you make it thick. And now you generate all your carriers here. And because it's thick and it has a field in it, so you absorb all your carriers here and the carriers can move and respond to the light in a fast manner. And therefore you get better response time. So most of your photodiodes then for application where speed is important, they're not PN junction. They are P and I and N, deliberately enlarging the region where you have high electric field. Otherwise, the electric field is high only in a smaller region here. And you enlarge it by making completely I. All of you rightly said that P and N region, you reduce the doping. So we have done that to the extreme case where we made doping equal to 0 in this particular region. Okay. So PIN photodiodes are very, very common and widely used here. All right. So this is, we have less time, so I'll skip this. Talk about all right, so I had an alternative derivation for this particular one, but I'll skip that. Skip too much derivation here. So the current in a PN junction diode then can be written as, this is a normal current, which is there when you apply a voltage or you in a normal PN junction diode. When you shine a light, you get an extra current, which is IR. Note that the light contributes to reverse current. We just saw that you generate carriers and it contributes to reverse current. So under dark, you get only the first term. When you shine light, you get the second term, an additional second term here. So under dark, if you measure IV characteristics, it looks like this normal diode. Under light, how will it look like now? This is a constant term coming from light, optical generation. So it will look like here. It will look like this here, right? Because the whole graph that you see here is pulled down by an amount minus IL here. And if you apply larger light intensity, well, you'll get larger current. That's what would happen. So this is something that you're already familiar with, but let me remind you, this is the part where we use a PN junction as a photodetector. Because here we apply a reverse bias to the PN junction. Our interest is in detecting very small amounts of light. Okay, and the current here then is sensitive to the amount of light that falls here. This part is, what is this part? This quadrant. This is photodetector. This quadrant. What happens in this quadrant? There's a difference between this quadrant and huge difference between this quadrant and this quadrant. In this quadrant, I is negative and V is also negative, right? You've applied a reverse bias and current is also negative. Your PN junction is, voltage is negative across the PN junction, current is also negative, PN junction is consuming power. Here, current is negative, the voltage across the PN junction is positive. What is the PN junction acting as? Source of power. So this is where it is, a solar cell. This is the place where PN junction acts as a solar cell. Very, very important part here. Okay, supplying current here. What about here? This quadrant? In terms of optical properties, let's talk about PN junction as an optoelectronic device, right? Where optical effects are there, electrical effects are there. Here we said photodetector. Here we say solar cell. What about the first quadrant? Photodiode is here. Photodetector is photodiode. Huh? LED. This is where you have an LED. Why LED? Well, what do you do in forward bias? You inject an electron and you inject a hole. The electron and the hole recombine. The excess energy is given as a photon. So that's where it's acting as an LED. And the conventional PN junction diode, in a normal application, which is a rectifier application, which quadrant do you use? Well, you use these two quadrants, right? As a rectifier. So normal PN junction is a rectifier here. It's an LED here. Not only LED, but if you take, the difference between an LED and a laser is nothing but the difference is LED with some mirrors and all that to make the light coherent. Then you get a laser here. So LEDs and lasers are here. PN junctions being used as LEDs and lasers here, as photodiodes here, as solar cells here, and in this particular region, of course, in forward and reverse, they use as a rectifier. Okay. So your basic silicon PN junction diode is being widely used for these three applications here, of course. Solar cell, photodetector, and rectifier. LED, of course, silicon doesn't emit much light, so it's not used here. So what I wanted to do next was to show you, because of the current importance of solar cell, talk a little bit about PN junction as a solar cell here. So if I focus on this part, can everybody see now that this one looks like here? This equation represents this equivalent circuit. This is your normal PN junction diode under dark. When you shine light, what do you get? This whole thing now represents PN junction under light. The light acts as a current source here, IL. And note that net current, if I look at a net current I, will be equal to this term. What is this term? This is the current in this particular diode, minus IL, which is this one. So that's how your PN junction acting as a solar cell looks like here. It's like a diode, but with a current source attached to it. Yeah. And this current source is coming from light. The greater the light, the more the current here. And then, of course, you want it to be used as a power source, so you connect a load here, RL. And now you can see here this current which is generated by light. Some current will flow through the diode, and you want most of it to flow through RL. And so your solar cell is delivering power to the load here. Okay. And now the issue is, what value of RL should I put to get maximum power out? Okay, so let's see here. So this is the equation here. The current that flows into your external circuit is minus IL plus ID. ID is this current here. All right. The power which is delivered to the load is minus I into V. Note the is minus because of the direction of the current that is assumed, minus I into V. So now, where is most of the power? Where should you bias your solar cell? If it is here, then I have a lot of current, but voltage is 0, no power. If it is here, I have a lot of voltage, no current. So again, it is 0 here. So you expect that if I look at power, the power is going to go like this here, where you start from this point and then you go towards this point here. So power that is delivered from the PN junction as acting as a solar cell will go in this particular manner. Somewhere there would be a maximum power delivered to that, okay, which we call it VM here. So the maximum power which will be delivered to your load will be equal to some minus IM into VM, whatever the VM is. And we can determine this because all that I have to do is note that I know IL value, let's say, and ID we know, ID is equal to IS exponent QV by KT. All we need to do is take a derivative of P with respect to V, equate it to 0, and we'll get wherever the maximum power occurs. Okay? So, there are certain parameters of a solar cell which are important. One of them is this parameter here. So what you do is you put RL equal to 0. You short the solar cell here. Note that diode and this is together a solar cell. Okay, they're not two independent entities. These together is a solar cell. And if you short the solar cell, you are here, and the current that flows here is what we call as the short circuit current. Very important parameter of a solar cell, short circuit current. On the other hand, if you remove RL, open circuited, some voltage will develop here. And this is called the open circuit voltage. So short circuit current, open circuit voltage. Is there anything else which should be important? The shape is important also. The shape of the characteristics. Because note, I can have several solar cells, same value ISC and VOC. In one case, you may have a linear line connecting it. In another case, you may have a more gradual going. An ideal case, maybe it goes ISC is flat and then abruptly goes to VOC. And different IV characteristics will give you different amounts of maximum power that you can get. So besides your VOC, besides your ISC, there's another important factor which is called the fill factor of the solar cell here. All right. So as we said, I'll stop after this. So as I said, maximum power is IM into VM. You know, somewhere at some VM you get maximum power. So what you do is IM by VM divided by ISC into VOC multiplied by ISC into VOC. This factor is what we call as a fill factor. This will always be less than 1 because IM will always be less than ISC, VM will always be less than VOC. We call it as a fill factor. So maximum power that you can get from a solar cell is fill factor, short circuit current, open circuit voltage. These are the 3 important parameters of a solar cell, which tells you how much power you can get from out from a solar cell here. So you have to know the short circuit current, VOC, and fill factor. Okay. All right. So we'll continue.